So we're trying to prove that the limit as x approaches infinity of sine x over x is equal to 1. And over here, in order to prove this, we'll first start out with a unit circle that has 3 shapes on it currently. It has if you can see from the blue line onward towards x degrees, that's our blue triangle. From the orange sector onward to the x degrees, that is our orange sector. And from the pink line onward towards x degrees, that is the area of our pink triangle. And we know that, well, we can obviously see that this blue triangle is smaller than our orange sector, which is smaller than our pink triangle. So that can be represented by this. Now, if we wanted to maybe make this into a more like quantifiable, with like numbers and stuff, we could figure out what the areas of these things are. And our area of our blue triangle, if we can see here, an area of a triangle is base times height divided by 2. So we know that the base of a unit circle, we know that this, our radians, every single radian is equal to 1. So we know that our base is 1. And we know that our height has to be this. And we know that our height for any degree, sorry, my cat is, okay, anyways. We know that our height of this has to be equal to the value of the y value of this degree, right? So we can represent that by saying it's sine of x degrees, because this is just the y value at x degrees. And we know that this is representative of the y value. So 1 sine of x and divided by 2. That is the area of our blue triangle is less than or greater than, less than or equal to the area of our orange sector, and we know that an area of a sector is radians squared multiplied by x degrees divided by 2. So we know that our radian is also equal to 1, because this is, again, a unit circle, and all radians are equal to 1. So our radian is 1 squared, as we can see here, multiplied by x degrees, or just x, divided by 2. Which can also be just written as x over 2. And our area of our pink triangle is equal to, okay, this one is a little bit confusing, but we can do this. So we know that tan of x, right? Tangent of x, or anything, if we use our SOHCAHTOA, we know that it's equal to the opposite over, TOA, adjacent. And we know that our opposite over adjacent here is our pink line, right? And our little base of 1. And we can just say that the pink line for now is, I don't know, n. That's our pink line. So tangent of x is n over 1. Well, if tangent of x is n over 1 and it's divided by 1, that means that tangent of x has to be equal to tangent of x, because there is no other option, right? It has to be that n is equal to tangent of x, so that this solution can be tangent of x is equal to tangent of x, right? So that it makes sense. So we know that n has to be equal to tangent of x. So we can write that as our little height. And we know that an area of a triangle, and this is our right triangle, is going to be the base, which is 1, multiplied by the height, which is tangent of x, divided by 2. Now we could just write this into simpler terms and remove all of these 1's and the 1 squared. So we get sine x divided by 2 is less than or equal to x over 2 is less than or equal to tangent of x over 2. Now, from here, we don't really want this divided by 2. It's making stuff too confusing, and because it is everywhere, we can just multiply all of these values by 2 because it's by 2, so that it's basically the same thing, so it keeps the same ratios, and then simplify it, right? So we get our sine of x is less than or equal to x is less than or equal to tan of x. Now, we want this middle portion to get as close, or we want this to become this. So the first thing that we can do is divide everything by sine of x so that we can later take the reciprocal of it. But for now, let's just divide everything by sine of x. Now for tan x divided by sine x, we could just go off into the side and do this. We know that tan x is equal to sine x over cosine x, and sine x is just sine x divided by 1. And we know for division, we can just multiply by the reciprocal, so it's 1 over sine x. Simplify, simplify, so this is going to be equal to 1 over cosine x is greater than or equal to x over sine of x is greater than or equal to sine of x and sine of x. That just means it's 1. Now, this is getting really close to this, but in order to make this sine of x over x, we're going to need to take the reciprocal. And now, taking the reciprocal, when we take the reciprocal of a problem that has stuff like greater than or equal to signs, we also need to adjust our greater than or equal signs for the reciprocal, so we're gonna need to flip them. Because think about it like this, right? So if I have 3 is greater than 1/3. Now, if we take the reciprocal of both, then it would be 1/3 and 3. But 3 is greater than 1/3, so it's going to flip around, right? So we get our 1 is, because 1 just stays the same, is greater than or equal to sine of x over x is greater than or equal to cosine of x. Now from here, we should start doing our limits, because what we're really looking for is the limit of this, right? So let's take a look into that. So limit of x goes towards 0 of 1 is greater than or equal to limit as x goes towards 0 of sine x over x is greater than or equal to limit as x goes to 0 for cosine of x. If limit of, okay, well, I like to graph things so that I can visualize them a little better. So we're just going to go off into here and graph a little. Here's this function, our blue triangle function. Well, if, let's say this is 1 and then this is -1. So if we're just going to graph it out first, and, oh my god. As you can see, our function is as x approaches 0 from both sides, and this is our 0, right? As x approaches 0, the y value is approaching 1, positive 1. So that just stays as 1. And then on the entire other side, this side, right, we're looking at it as, we know what a cosine graph looks like. And we know that it looks something like, if this was 1 and this was -1, it looks a little something like this, right? We know that as as it approaches 0, as x approaches 0 from both sides, as it's going this way and this way, we know that our y value is approaching this point of this y value of 1. So this limit is also going to be 1, positive 1, right? Positive. Okay, anyways. Well, let's think about this logically, right? If the limit as x approaches 0 of sine of x over x is less than 1, but it's also greater than 1, then that means it has to be 1, right? So this limit as x approaches 0 of sine of x over x has to equal 1 because there is no other option. We could graph this out, right? And we can see that this is kind of a compressing situation when we graph it out. So let's just graph it out right over here. And let's just graph out our blue function. Our little blue triangle function. And then the cosine. Right, our cosine function. And then what it ends up looking like is that our sine of x over x function ends up looking a little something like this, right? And now this looks really confusing as a big picture, right? This, you don't know what's going on. But I want you to just zoom in a little on this part, right? So if we zoom into that a little, we're going to look at so that this is our cosine of x function, this is our 1 function, and then this is our sine of x over x function, right? So, if we look at that, right, we can see that from here, both of these values come to a point over here. Both of the values of as cosine of x goes to 0 and as 1 goes to 0, y equals 1 goes to 0. They're both values at 1. Now we know that for sine of x over x, like y equals sine of x over x, we know that for this point of 0, it's undefined. It has a hole because sine of 0 over 0, you can't divide by a 0. There is a hole there in our final graph. But for now, while we're looking at this, let's just look at it as it is for now. And we can see that this cosine graph is compressing our sine graph so that it goes towards 1. And our y equals 1 graph is also compressing from the upwards motion as sine of x goes to 1. And because both of these values are 1, this sine of x over x graph is going to approach 1, even though there is a hole there, right? So we can represent that by a little hole. Even though there is a hole there, the actual graph might look a little something like this. But because of these compressing functions, we now know that the limit as x approaches 0 for sine of x over x is equal to 1 because of the compressing factors from cosine, y equals cosine of x, and then y equals 1.